Okay, since we have an infinite solution for both of them, we need to check for the convergence. Although this is a mathematical approach, and in physics or even like engineering, you don't really care about this, but I'm gonna do it because it's really cool. So for checking convergence, we need to do the ratio test. So the limit n goes to infinity, because this is a powered series, we can check for the radius of convergence. A sub n x to the n plus 1 divided by a sub n minus 1 x to the n minus 1. Yeah, that's right. Okay. So we just said limit is n goes to infinity. We'll have an x squared a sub n over a sub n minus 1. Now, to find this ratio, we can use the generating function that we had, because we had an in terms of like an minus, it should be minus 2, I guess. We had an in terms of an minus 2. Okay, so we can use the generating function to notice we have limit from n goes to as n goes to infinity x squared over the generating function was n squared plus 3n for the ans. And notice as n goes to infinity, this denominator will always go to 0 for all x values. So it converges, so the radius of convergence is infinite. So it converges everywhere for all x values. The ratio test says it converges because 0 is less than 1. This less than 1 is necessary to prove convergence. Okay, this was for the ANs. ANs are nice. What about the BNs? So we have y2 of x to just be sum n equals 0 infinity bn x to the n minus 2. Okay, and then we can write this as sort of b naught 1 over x squared plus 1 half plus, I think we have, let's see, minus x squared over 8, and it's infinite. So now to check for the convergence of this guy, do like a similar approach, the ratio test. So we have bn x to the n minus 2 divided by bn minus 2 x minus 4. Use the generating function for this, x squared over n squared minus 3n. Now it might be easy to say, whatever, it's going to it's denominator going to infinity, x shouldn't be a problem, it should go to 0. But notice it doesn't hold for all x. This doesn't go to 0 for all x. Notice if you plug in like x equals 0 into this, 1 over x squared will blow up to infinity. So there's only convergence for x not equal to 0. So everywhere else it converges. Everywhere else it's going to equal 0, which is less than 1. So yeah, I think this is important to so this is how you do it. Sometimes your generating function may not be this simple, in which case you need to find a dominant term. If you have, say, a generating function with n minus 2 and n minus 1, you need to find the dominant term and do a sort of real analysis kind of stuff. I'm going to do real analysis, but not now, in the winter break maybe. Now, one thing great about the solutions given to us by this approach is if you say let a naught be 1/3, y1 of x will be 1/3 x minus x cubed over 10, x to the 5th over 280, and so on. And this is the spherical Bessel function of order 1. So it's a special function which I believe pops up in like quantum mechanics all the time, because you're solving differential equations and then using Sturm-Liouville theory to convert them into ordinary differential equations and then solve them using this approach like we've done. The graph of this, I don't want to like do too much detail into this, is kind of like this. The oscillations are non-periodic and they're getting smaller. And now the other guy, y2 of x, if you let b naught to be -1, is negative 1 over x squared plus 1/2 minus x squared over 8, and so on. And these guys are the Neumann function, Neumann or Newman, whatever, of order 1. And the graph of this, there's a distinct characteristic you might want to see, is that it's blowing for 0. It's like vertical asymptote here, and then non-periodic oscillations like the last guy. Yes, so you can only generate these guys by using Frobenius method for solving differential equations. You can't do this with conventional methods because these functions themselves are special. They're non-elementary. They don't have a closed form, as it were. So in this way, I think this is really fundamental. This is one of the basic tools you should have, even if you don't know any like stylish methods like the method of quadrature, or even Laplace transforms, or even, I don't know, like Bernoulli's method for solving differential. Check that video out. Many people haven't watched that. It's interesting. So this is how you. So this would be one way to approach, and only as long as it's homogeneous. Okay, I hope this video is not too long, but I just wanted to prove a point that if you have a differential equation that's like this, then if you use the Frobenius solution on this, because you can add y on both sides and get a homogeneous equation, then you would generate the Taylor series for the sine and the cosine, because this has a solution of sine and cosine. So, and just to show that, like, if you have an elementary solution, you can get an elementary solution by using Frobenius solutions. This is just an example, and I'm not going to do this. I'm just going to run through it. So if this differential equation, again, notice it's linear. It has these like polynomial coefficients, and it's homogeneous. So you can use Frobenius solution, and that's what I've done here. So I just plug this into my equation, and I have this big thing. And I'm just going to regroup some terms. So notice the x to the n plus s minus 1 I can regroup together, and n plus s, x to the n plus s is separate. Since this guy is like trailing behind by 1 from this guy, I need to expand once. So I did c naught s squared x to the s minus 1 plus c sub n, and then just this guy starting from 1, and this guy is as it is. And then we can re-index this second guy with c sub n minus 1, 3 minus s, n minus s, and x to the n plus s minus 1. Notice the powers are the same, so we can group them up. And noticing that this guy is your indicial equation down here. Assuming c naught is not equal to 0, you have s equals 0 as for both the cases, because it's a perfect square, s squared. Okay, so you just have one case to deal with. That's nicer. So this is the one case. Call this a naught. It's a sub n, x to the n. With your generating equation, you can use this, clubbing both of these as a generating equation down here. and then plug in s equals 0 because that's the only case. You get this a sub n minus 1 times n minus 3 over n squared is equal to an. You have negative 2 a naught, a2 is a naught over 2, a3 is 0. And then since a3 is 0 and we have n minus 1 dependence, everything after a3 will depend on a3. So a4 will have a3 times 1 over 4 squared. Since a3 is 0, everything after a3 will be 0 because of this generating equation. That's what's powerful about this. The generating equation can dictate what happens next. And since our series terminates, everything else is 0, we can just write these first three terms. A naught minus 2 a naught x plus a naught times x squared over 2. And that's your solution. And also notice one thing, since this was a first order differential equation, we just have one solution and it makes sense. My bad, it's not first order, it's not first order, it's second order, but still it has one solution because, well, sometimes like the second solution's like just the trivial solution, or it's some complex solution, in which case s would be complex, but it's not the case here. It's either the second solution's like 0 or it's some like constant which got multiplied with the a naught here, which sort of got added with the a naught here. Or if we can check, if we had known the Wronskian method, we would have found the second solution given the first one, and that's an interesting approach. I'm going to show you this in the next video. But let's see. I think that this is important because the series terminates here. Not all series generated by the Frobenius method should be infinite. And again, this converges, of course, for all x. That's it for this video, guys. Please like and subscribe to my channel, guys. Recommend me to your friends. Spread the word of Gamma Diagram in the math community. And in the meantime, stay home, stay safe, keep doing math. I'll be back with Wronskian method and some more cool stuff, some more integrals. So peace out.